everyone, welcome back to a new video. Today's topic is about quicksort. Quicksort, a comparison-based sorting algorithm that utilizes the divide and conquer approach. So, how does quicksort rely on dividing and conquering an array in order to sort it? The following example demonstrates what I was talking about. As you can see, there is a group of people that are asked to stand according to their height, where every one of these people is asking the question, where shall I stand? To answer this question, this guy shall compare their height with the other people in the group. People of height greater than this guy's height shall stand before this guy. And people of height lower than this guy's height shall stand in the front of the queue. So quicksort, as I've told you in the introduction, relies on the divide and conquer approach. So I want you to think of quicksort as two parts. Part which is responsible for dividing, which will be represented with recursive codes, and part that is responsible to conquering the problem and solving the problem, which will be representing the partitioning that we shall see right away. Now let's take a look on the conquering side of quicksort. You can see here an array A composed of n equals 7 elements. I want you to associate these numbers in the array with people's height. Imagine it as a scale to represent people's height. We want to choose a random number or a random person and partition the array in a way where the heights of the people that are less than this guy are shown to their left, and the heights of the people that are greater than this guy are shown to the right. So, how shall we do it? The partitioning algorithm I'm gonna use to partition the array A is called the Lomuto Partitioning Algorithm. There are other partitioning algorithms, but for now, let's stick to this one. You can see here the Lomuto algorithm for partitioning an array A. First, we pick a pivot which we denote the last element of the array. You can pick any pivot you want from this array and swap it with the last element. For example, if we pick 5, we have to swap 5 with 6, and 5 is now the new pivot. But for simplicity reasons, we shall use the last element of the array as our pivot. Now let us simulate the Lomuto partitioning on the array A. Here, the chosen pivot is 6. We first initialize a pointer pointing here, an element before the beginning of the array. We start a for loop for j equal L, which is the beginning of the array, to j equals R, which is j less than R, which is the last element of the array excluding the pivot. If we found that A at index j is less than or equal to pivot, we increment I by 1 and we swap array of I with array of j. So let's start. First I and j are pointing as shown. A of j, which is 8, isn't less than or equal to 6, so we continue iterating. 7 as well is greater than or equal to 6, so we continue iterating until reaching 5. 5 now is less than 6, so we have to swap 5 with 8. But first we increment the I pointer to point at 8. We continue iterating over the for loop until reaching 4. 4 now is also less than 6, so we need to swap it with 7. We increment I by 1 and we swap. We continue also iterating, reaching 3. 3 is less than 6, so we swap 8 with 3. Now I is pointing at 3. We continue iterating, reaching 2. 2 now is the last element to check. 2 is less than 6, so we swap 2 with 7 after incrementing the I pointer. Now we have reached the end of the for loop, so now we should place 6 in its correct position, which is to swap 6 with I plus 1 which is 8. So now we swap 6 with 8 as shown here. This will ensure that all the elements to the left side of 6 are smaller than 6 and the elements to the right side of 6 are greater than 6. Now let's see the dividing side of the quicksort approach. We first, in the previous example, placed 6 in its correct position. We should divide the array, continue with the array, and place every element in its correct position. So, how shall we do this? After placing 6 in its correct position, we are left with this part of the array and this part of the array to sort. We repeat the same process of partitioning to this part of the array and this part of the array. For example, here the pivot chosen is 2. We repeat the same process of the Lomuto partitioning and place every element smaller than 2 to the left side of 2 and every element greater than 2 to the right side of 2. This will ensure 2 now is in its correct position. The same goes to the subarray composed of 7 and 8. Now after running the Lomuto partitioning on the subarray, 2 now is in its correct position, which is at the beginning of the array. So we are left with this part of the array to sort, which is 4, 3 and 5. We shall use the same approach we did in the Lomuto partitioning to choose a pivot and place it in its correct position. Now after running the same algorithm for the rest of the sub-problems, we shall see that every element now is in its correct position, starting from 2, 3, 4, 5, 6, 7 and 8. Now you can see the two parts of quicksort, which is conquering and dividing. Conquering is the algorithm we have discussed before, but we now added a return I plus 1, which we will now see what is the function of returning I plus 1 here. Quicksort first takes an array A and 2 pointers L equal to 0 and R, which is at the end of the array initially. First, it checks if L is less than R in order to proceed with the algorithm. It calls the Lomuto partition, which will first choose a random pivot or the pivot at the end of the array and partition the array according to this pivot. When it ends, it returns the position of the sorted element that is now in its correct position. Q here represents the position of the sorted number, the position where the number must reside in the array. So now, what am I left with? I am left with the elements that are from L to Q minus 1, which are the elements to the left side of the pivot, and the elements to the right side of the pivot, which is Q plus 1 to R. These two sub-problems are going to be solved using the same algorithm, which will also be called and choose a pivot and place it in its correct position until L is no longer less than R, so it shall stop. Now we shall discuss the time complexity of quicksort. You can see the recurrence relation of the best time and the worst time complexity for the quicksort. The best time is when the partitioning is balanced, meaning I'm placing a pivot where the elements that are less than the pivot and the elements are greater than the pivot are of equal number and size. So the recurrence represented is 2n over 2 because we have two sides, and n over 2 because we are partitioning in half, plus big O of n, which is the time responsible for partitioning the Lomuto partition. However, the worst time complexity is T of n minus 1 plus big O of n. Big O of n here is also for the Lomuto partitioning. However, T of n minus 1 meaning it's not balanced, which is meaning we are placing a number where all the elements are greater than the number. There are no elements which is less than the number, meaning the recursive tree is not balanced and it's weighted on one side. So this recurrence relation, if we want to solve it, must simplify to big O and square. However, the best case scenario will simplify to n log n. Yet, if we want to discuss and deduce the average case scenario, we rarely encounter a tree which is not balanced. So the average case scenario is closer to the best case scenario, which is big O of n log n. This has been the CS Tutor. If you have any questions, put them down below. See you next time.